Hello, my name is John Perham from the School of Mathematics and Statistics at the University of New South Wales, and I hope to tell you in the following 10 or 15 minutes something about the Hodgkin-Huxley equations. Okay, so let's carry on and we'll get rid of Last Peter. Anyway, the Hodgkin-Huxley theory is well, we can upload the title page and the abstract of the paper, and you can see a couple of things about it. Firstly, it's from 1952, and this will be an important number in the story I'm about to tell, and you can see that it involves 45 pages, which is a pretty long paper by any stretch of the imagination. And it reported research on a possible mechanism for the complicated electrical behavior of nerve cells, mainly squid axons. Now, this work has been cited, believe it or not, 13,554 times since its publication in 1952. And the authors, together with Sir John Eccles, were awarded the Nobel Prize for Physiology and Medicine in 1963, mainly for work contained in this paper. So the work contained in the article is extraordinary from many points of view, not the least of being the large number of figures describing significant computations done at the time and place when real computers were just appearing for the first time. In fact, at the time when the computations must have been performed, 1951, they were only possible on machines at Manchester, Cambridge and MIT. And there are three phases of the work, each at different levels of complexity. So the first phase is what's called the voltage clamp. The voltage clamp involves a circuit board prepared by Cole and Marmot, I believe, Hodgkin and Huxley built a model for the absorption of, sodium or potassium and sodium ions along these lines. So M prime of T is one of the parameters associated with sodium ions, and you can see that it satisfies this linear differential equation. And likewise, H prime of T is also for sodium ions, and N prime of T is for potassium ions. And they're related to the sodium and potassium and sodium conductances, namely GK for potassium is equal to GK, a constant, times the value of NT to the fourth. And GNA is equal to a constant times M cubed and H of T. I don't want to go into where the thoughts of Hodgkin and Huxley on why these numbers should be so. Anyway, by measuring the sodium current in squid axons when the membrane was clamped at various values, they found that the results could be fitted tolerably using these equations. So alpha n was fitted to be 0.01 times this function of the potential, and beta n was fitted by this function. So if we go back up here, we can see that that's alpha n and beta n here. And then by measuring the sodium current in squid axons when the membrane potential was clamped at various values, they found that the results could be fitted tolerably using these expressions here. And there we go. And there we go. and there we go. So these are found by fitting the experimental measurements to the solutions of those differential equations. Okay, anyway, since the three differential equations for fixed voltages, if we go back here, we can see that they're linear, so they can be solved analytically, so we don't need a computer to do this. Well, not very much. So that was the first part of the analysis. It's called the voltage clamp calculation. This is not true for the next part of the computation, where a shock depolarization is applied to the resting membrane. And if the depolarization is sufficiently strong, the membrane depolarizes completely before slowly returning to its resting state. In this case, the potential V in the fitted forms of the alphas and betas becomes V of t, so that, put a comma in there, so that the differential equations for the ionic currents become nonlinear, as does the differential equation I of t equals the capacitance times the temporal derivative of the potential times this. Because the equations for n of t, m of t, and h of t now depend on v of t, we thus have to solve four nonlinear, fully coupled, first-order differential equations. So how was this done? Well, the first clue is provided by the authors, who noted that they used an algorithm due to Douglas Hartree, published in a very noble, in fact I think it's the second oldest scientific publication, but now obscure journal, the Manchester Memoirs of the Literary and Philosophical Society, of which the Society kindly scanned me a copy, whose first page can be uploaded using this. So what do we see about Hartree? Well, we don't. It's by Douglas Rayner Hartree, PhD, Fellow of the Royal Society, from this article submitted in 1933. So this is the article that Hodgkin and Huxley claim was what they used to solve their equations numerically. But curiously enough, if you see here, the equations that Hartree focuses on are second-order equations of this kind. He does, to be fair, provide a brief discussion of how it might be applied to first-order equations. Now, this article is from 1933, before any computers, so whatever he discusses in his paper will be done with some kind of desk calculator. This paper was written well before the first real computers, which appeared around 1948 in Manchester, Cambridge, and MIT. So how did Hartree actually do his calculations? Well, curiously, Hartree and a student, Arthur Porter, built a differential analyzer out of Meccano in 1934, which is on show in the current Turing exhibition at the London Science Museum, and we can upload a picture of it from that exhibition here. And I believe there are 8 of these so this is, according to the exhibition, this is a reconstructed machine for solving complex mathematical equations, originally made in 1934 by mathematician Douglas Hartree and his student Arthur Porter from the construction toy Meccano. And it was one of the first electromechanical computers. So it used the movement of shafts and gears as the physical analogue of the mathematical relationships. Well, anyway. So later digital computers electronically manipulated the numerical values themselves. So who was Douglas Hartree? At the time he and Porter built this machine, Hartree was Professor of Applied Mathematics at the University of Manchester, until 1937, when his talents were enlisted in the war effort. And these talents included the ability to generate numerical solutions of differential equations, which was actually Hartree's main scientific activity. Well, at the end of the war, the main players from the Colossus computer, which had cracked the German Enigma coding machine, moved back into academic life, mainly to Manchester and Cambridge, where two of the world's first von Neumann computers appeared in 1948, by which time Hartree had been appointed in 1946 as Professor of Mathematical Physics at Cambridge. Well, on the development of the EDSAC computer at Cambridge in 1949, the Wikipedia entry on Hartree remarks, Hartree worked closely with Wilkes in the development of the machine for a wide range of problems, and most importantly, showed users from a number of areas in the university how they could use it in their research work. So anyway, so that was the second part of the problem, and now we get to the third part, and the most challenging part, which involved the propagated action potential. And in this, you've got to imagine a nerve cell, which is basically a long, thin cylinder of membrane, and and a small part of the membrane is subjected to an electrical impulse. And this will result in a potential difference, which now is a function of position and time, propagating in both directions away from the stimulus along the squid axon. The result is the partial differential equation here, so that all the variables now become functions of position along the axis and time, and since the result appears to be a linear wave, v of x plus or minus theta t, Hodgkin and Huxley sought a wave-like solution to this equation for which the potential satisfies this now. Well, the only problem here is that the wave velocity theta is not known in advance, so that the solutions of the four differential equations have to be iterated with respect to theta until the solution converges, so that f of v of t tends to 0 as t tends to infinity. So how do I fit into this? Well, my only comparable experience occurred at the University of Sydney in 1965, when I tried to solve the three first-order differential equations for the shape of drops forming in the presence of gravity on an electrical calculator. I was trying to solve them on the electrical calculator. I soon gave this up and tried to solve the equations on the KDF-9 computer at the University of Sydney. Later, I completed the solution on the Atlas computer at the University of Manchester when I began there as a PhD student in 1996. The numerical solution of these equations was first published by Bashforth, who was a priest, and Adams, who was a numerical analyst, in 1883, with the actual computation by Bashforth taking several years. So how did Hodgkin and Huxley solve these equations? The most complete response has been given by Kenneth S. Cole in 1968, in which he gives a more complete description of the algorithm and reports conversations about what happened at Cambridge. Cole remarks, Hodgkin and Huxley tried to use the then current automatic computer at Cambridge in their original work, but unfortunate mistakes and delays forced them to rely entirely on a desk calculator. Cole continues, yet Huxley has admitted that it took about a day to compute a single space clamp response and a week for a free propagating impulse, while Hodgkin has often emphasized his colleagues' amazing speed and accuracy with a desk calculator, presumably because he spent most of the war doing this kind of stuff. Well, some more information can be found on this problem from the informal history of the Cambridge Computer Laboratory, which can be seen at this place here. There it is. Here we go. Of particular interest is the item below for the 1948-49 period. Research on programming methods under Wilkes, including definition and refinement of initial orders due to Mr. Wheeler, closed subroutines, also Mr. Wheeler, and building of a library of subroutines, all laboratory members interested in programming, plus Professor D.R. Hartree. So, what do I believe? Well, if we take Cole's observations as correct, and that Huxley had tried to perform the calculations on the EDSEC computer at Cambridge, then I find it very strange that there is no mention anywhere of a meeting between himself and Hartree, especially as scientists are still working on the Hodgkin-Huxley equations. And from an understanding of Hartree's work, I would have expected that by 1951 he would have developed subroutines which could have been routinely adapted to solve Hodgkin and Huxley's differential equations numerically. I believe that it's also relevant, the reference given by Hodgkin and Huxley to Hartree's work was dubious, since it deals with differential equations of a different type. So I guess that since everybody involved is dead, we should let them lie in peace.